All right, folks, we're going to conclude this chapter with a quick look at what is called surface area. This will be surface area, and we've seen how to find volume of solids of, revolution. Well, this is going to be the surface area. So, section 6.3 and 6.4. That's where we learned how to find the volume of a solid of revolution. We learned the disk method, washer method, and the shell method. This section, we're going to take a brief look at finding the area for a surface of revolution. So a quick definition is that if you take the graph of a continuous function and you revolve it about a line, the surface is called a surface of revolution. And, I'm just going to get on with it on how we find the area for a surface of revolution. So the definition is, y equals f of x. It has a continuous first derivative on closed interval a, b. Then the area, or the surface area, of the surface of revolution formed by revolving the graph of f about a horizontal or a vertical line is given by... Well, there it is. Surface area equals 2 pi the integral a to b p of x square root 1 plus f prime of x, squared dx. There's some familiar looking stuff in there. P of x, it's nothing more than the distance from the graph of f and the x-axis. Or, I'm sorry, the axis of revolution. So P of x is the distance from the graph of f to the axis of revolution. Likewise, if x is a function of y on closed interval CD, then we have the surface area is 2 pi integral c to d p of y square root 1 plus f prime of y quantity squared dy. And yeah, here p of y is the distance from the graph of g to the axis of revolution. So... let's look at a quick example, and there's only going to be one example, that I'm going to look at here, and this is it. Find the area of the surface of revolution when y equals the square root of x on the closed interval 1 to 4 is revolved about the x-axis. So I'm going to head off to the chalkboard and work through this example. All right, this example of finding area of a surface of revolution. We're going to find the area of a surface of revolution when you take y equals square root x on the closed interval 1 to 4, and you revolve it about the x-axis. We know how to find the volume of that solid of revolution. Now we're going to find the area of the surface. This is the formula. 2 pi integral a to b p of x square root 1 plus f prime of x squared dx. So I've gone ahead and preloaded some stuff on the board. This is the graph. I've labeled what p of x is because we're revolving it about the x-axis. So p of x is square root of x. And we also need to know the derivative of our function. Well, the derivative is 1/2 x to the negative 1/2. So let's start to attack this. Yeah, these problems are rigged, so we can do them. We integrate, let's see, the limits of integration are 1 to 4. P of x is square root x. The derivative, well, we have the derivative is 1/2 x to the negative 1/2. So that's, let me write that as 1 over 2 square root of x. And then that has to get squared. So cleaning up a little bit, we have square root of x, square root of 1 plus... So when you take 1 over 2 square root of x and square it, you get 1 over, 2 squared is 4, square root of x squared is x. Okay. Yeah, this is rigged so we can do it. It looks like a really difficult integration problem right now, and it kind of is. But let me focus on what is under the square root. So let me come over here and let me write down what's under the square root. So what's under the square root is 1 plus 1 over 4x. Now if you get a common denominator, this would be 4x plus 1 over 4x. So that's what's under the square root. Well, you know what? That's under the square root. Let's use a property of square roots. When you have the square root of a fraction, you can rewrite this as the square root of 4x plus 1 over the square root of 4x. So that's the square root of 4x plus 1. Let me use another property of square roots. You have the square root of 4x. That's the square root of 4 times x. Well, the square root of 4 times x you could rewrite as the square root of 4 times the square root of x. And you know the square root of 4 is 2. So we've done a little bit of simplifying here. So let me rewrite this before I lose track of what's going on. So over there on the side, we just kind of played around with this radical, and after doing some algebra, we got this radical to the point of being the square root of 4x plus 1 over 2 times the square root of x dx. Well, isn't that convenient? Isn't it convenient that in the integrand we happen to have a square root of x, and down here we have a square root of x. So isn't it convenient that they would cancel out and just leave us with the square root of 4x plus 1 over 2? You know, we could actually take this 1/2 and rip it out front to get pi integral 1 to 4, just square root 4x plus 1, which I'll write as 4x plus 1 to the 1/2 power. Then a basic u substitution. Allows us to finish off the integration. So let me do the u sub. Let's see, this would be a times, I got to get a 1/4 out there, so u to the 1/2. So pi times 1 over 4, antiderivative of u to the 1/2, add 1 to the exponent. Got to remember to get the 2/3 reciprocal of the new exponent here. So let me multiply this together. 1/4 times 2/3, that's 1/6. So I have pi over 6. Resubstitute my u. Evaluate this from 1 to 4. And so let's see. 4 comes in, so that's 16 plus 1, that's 17. So I'd have a pi over 6. 17 to the 3/2, and then minus pi over 6. Let's see, the 1 comes in here for x. 4 times 1 is 4, plus 1, that's 5. So that's 5 to the 3/2. I suppose you could rewrite that. I'm just going to go one more step. I'm fine with this. You can factor out the pi over 6. And the 17 to the 3/2, you could write that as 17 square root 17. And the 5 to the 3/2, you could write that as 5 square root 5. And well, I ran out of room, so that's as far as I'm going to go. So that's it. There was just one example in this section. I don't have a whole lot of problems for you to do, but you can now try to do the very few problems that I've asked you to do. Thanks for watching.